Hello, and welcome to this week's Ethical Dilemma in Science. We're going to take a look at drinking recycled wastewater and see if this is creating a circular cycle of human water usage. So this week's Ethical Dilemma in Science is based on an October 2022 article in the New York Times stating there's something in the water in Virginia. Before you say yuck, wait. And so this is focusing in what is going on in Virginia, but we can see that this is a problem that extends throughout the United States. And to be honest, it extends beyond the United States to the entire world. About 1 out of 4 people globally do not have access to a safe source of drinking water. And this is associated with the fact that with an increased population, we're seeing a heavy demand for water. We are seeing a change in the climatic patterns that are contributing to greater droughts. And because of this, we're using up groundwater faster than it can be replenished. In Virginia, they're drawing water off of an underground reservoir, and they're using about 155 gallons of water from this reservoir each day. And the natural replenishment, the natural process of returning water to that is much, much slower. It's estimated that if they stop drawing the water off right now, it could take hundreds or even thousands of years for it to refill completely. And so the idea is that they are going to go and treat used water, basically treat water that had been used in a variety of sources, and take that water from the sanitation systems, bring it back to drinking water quality, and then return it back to the reservoir. And in doing so, instead of allowing this treated water to go into the Elizabeth, James, and York River, they would be ultimately returning it back to this underground reservoir. And this is something that is being done already in other locations around the United States. And this is in response, or in addition to mandatory water restrictions that are involved with cutting down consumption. And so problems associated with drawing off water from these underground reservoirs is that the water that would normally be present within the reservoirs, providing some structure to these underground structures, if it is no longer there, you run the risk of the ground sinking or potentially collapsing, as well as at least in Virginia, fairly close to saltwater sources. Without this fresh water within these underground reservoirs providing pressure, there's a risk that the salt water would infiltrate into these reservoirs and basically take this freshwater source underground and convert it into a saltwater contaminated source, which would be very difficult to use for human consumption. So before we can understand what's involved with restoring water to these underground reservoirs by pumping treated recycled water into these locations, it's first necessary to understand that normal hydrologic or normal water cycle. And so this diagram is showing the traditional view of the water cycle. And so you can have surface water, and so this may be lakes or rivers. We've got saltwater sources over here, illustrated by the ocean or potentially kind of a larger lake. I'm looking at this in the form of salt water. But basically what happens is we've got evaporation that's going to be occurring. So water evaporating, kind of going up into the atmosphere. When that water vapor, that evaporated water is up within the atmosphere, it is going to condense down into clouds. So basically clouds are condensed water, and then under certain conditions, that water basically condenses, becomes so heavy that it's going to drop out of the atmosphere. It's going to go from a water vapor into drops of water, and it's going to come down in the form of precipitation. And that precipitation, based on the weather pattern, may be rain, as we're illustrating kind of over here. It could be snow, as we kind of see over here. But basically that rain or snow is going to end up back into that water supply. And so we've got this process of evaporation going up into the water vapor into the air, clouds condensating, and then precipitation coming down. Now, in addition to this kind of traditional kind of path of water, we've got these kind of reservoirs in terms of ice and snow that may melt off and run off and kind of replenish this, kind of taking a look at the surface water flow. Now, in addition to the surface water, we're going to have these underground reservoirs. And so what we've got here is that water within these surface water locations, within these lakes and rivers, even kind of rain runoff is going to get into the soil. It's going to flow down into the soil and then end up in locations as these underground reservoirs down here. And it's these underground reservoirs that are going to be tapped into with wells, water wells, in a variety of locations. Now, if we focus on these underground reservoirs, what we can see is that about 25% of the water comes from groundwater sources, and about 75% of the water is going to come from surface water. Now, surface water, water in the form of lakes or rivers, is often going to be limited in a variety of areas. So there are locations around the planet that don't have surface water readily available, and surface water is highly dependent upon the availability of rain. And so an extended drought is going to make it very difficult to replenish surface water supplies. Now, about 25% of water usage is coming from groundwater, and these are going to be in the form of freshwater aquifers, illustrated here in these blue kind of regions. And so what we can see is that these are basically locations where water has percolated from the surface down into kind of these deeper regions within the soil, and it generally is going to be found in areas where you have a lot of maybe silt, maybe gravel, sand, or even things like porous rocks like limestone and sandstone. And so we've got these sources of water, but they're only going to be replenished when the water flows from the surface down deep within these areas. And so they're replenished by water flowing down. Now, in some cases, we've got these regions, which are basically called confining units, which are going to kind of restrict the flow of water down within the ground. And so refining units would be things like clay, like shale, even things like unfractured granite. And the water can't penetrate through that. So in this case, we've got an aquifer sitting upon one of these confining units here, and that's preventing the water from getting down into a lower area. So we've got a source of water, whether that source is going to be an aquifer, if we're taking a look at a ground source of water, or a lake, if we're taking a look at a surface water. In the drinking water cycle, so basically your municipal water supply, the water is going to be drawn from that reservoir into a system, often going to be purified in some way, and then moved into a storage location. And so the water tanks that you may see, kind of sitting along the horizon, are basically these elevations, elevated structures associated with water storage. And because they're in an elevated structure, the water is able to flow down out through a series of pipes. And that force of the water from that elevation is going to drive it into, or force it into, our homes. Now, ultimately, once that water has been used, it's going to go into a sanitation system, into a sewer system, where the water is going to be kind of returned either into a wastewater treatment plant, or it's going to go into a septic system. And in the septic system, you're basically going to allow the used water, the sewage and other materials, to basically end up in a system, and it is going to kind of filter out the water. And so the water is going to infiltrate into the ground, hopefully leaving behind all of the harmful and contaminants that would be found within it. Within a wastewater treatment plant, we're not allowing it to simply percolate through the ground. We're going to be treating it in some way ultimately to the point where we're going to remove the contaminants, remove the things that don't need to be in the water, shouldn't be in the water, and then discharge that, often discharging it back into a surface water source. So returning that and flowing it back into a lake or a river that ultimately may be used as a surface water source for that same municipality or another municipality further downstream. So the traditional way of treating water for drinking is to take the water from its source. So again, this may be a surface water source like a lake or a river, or it could be an underground reservoir, but the water is going to be brought into a treatment plant. And so we're looking at a municipal supply as opposed to a well that would be supplying an individual home. The first thing that's going to happen is a process of coagulation where we're going to add some chemicals to it. And the chemicals, they may be salts, they may be aluminum, maybe a little bit of iron, are going to clump together with the dirt and other dissolved particles that are coming from that water source. What's going to happen is that it's going to cause them to start to form little clumps in the flocculation chamber over here. We're going to mix those clumps up gently, and that's going to cause those small clumps to become larger and larger clumps. And ultimately, those large clumps are going to go into a sedimentation tank so that those heavy clumps of dirt and debris and other materials suspended within the water are going to settle out. And so we're going to draw off these kind of superficial layers of the fluid, superficial layers of the water that are not carrying these clumps of debris. And that then is going to be filtered. It may flow through kind of a sand bed, it may go through a gravel bed, maybe even goes through something like activated charcoal, which is going to remove additional materials that are suspended within the water. In some cases, it'll run through an ultrafiltration system where it'll run through a series of structures that have very fine pores that will only allow for water to flow through it and maybe small ions, small materials, minerals that would be normally found within our drinking water. In other locations, they may use a reverse osmosis system where they're using a much more complicated system to pull the materials out of it. Ultimately, they may then go into a disinfection system where they will add chemical disinfectants, something like chlorine, or possibly shine ultraviolet light on it to kill any remaining parasites, bacteria, or viruses that are still within the water. At that point, it should be a drinking water quality of the water, so relatively pure, and then it will go out into a distribution. So in this case, we can see a water tower here. So the water is going to be pumped up into the tower, kind of stored within that tower, and then the force of gravity will allow for that water to flow back down and out into our individual homes out within the community. Now, if we take a look at the sanitation treatment plants, they're doing pretty much the same basic thing as the traditional treatment plants going into a water supply system. We're going to have the raw used water coming in, and so that may be including, water from your sink, water from your garbage disposal, water from washing dishes, as well as sewage coming, from the toilet, in essence. It's going to go through a series of filters, and so they're going to kind of screen those materials coming out. They've got a grit chamber and a settling tank, basically to allow for those particulate matters to settle out. They're going to go through, they're going to aerate it and treat it in a variety of ways. But ultimately, the goal is to do pretty much the same thing as that initial treatment, to take out those materials that shouldn't be found within the water and leave a pure water behind. Now, in terms of a sewage treatment plant, we've got that raw sewage. We've got kind of organic material that may be found within it. We may have, like fertilizers, so nitrogens and phosphates. All of those materials are going to precipitate out in the form of sludge. And that sludge then can be collected, could be processed in a variety of ways, often kind of used organically, using bacteria to break it down into something that can either be disposed of within a landfill, or in many cases it can be used, once it's been sterilized, it can be used on croplands, pasture lands as a form of fertilizer. Ultimately, what we want is a disinfected water up here that is drinking water quality. And under normal circumstances, once this has gone through a treatment plant, this water is then going to be discharged into a river, into a lake, or into an ocean. And so that would be basically, a groundwater source that another region may be using as their water source. So as we can see, there are a lot of things that can affect the drinking water, whether we're getting it, in a bottled water, whether we're getting it from a municipal supply, or potentially if we're drawing it from a well. Now, the Environmental Protection Agency within the United States sets standards for drinking water. And so they take a look at over 90 different contaminants and sets levels of those contaminants that can be found within the water. Now, in some cases, those contaminants need to be completely eliminated from the water. In other cases, it has to be at such a low quantity or such a low concentration within the water that it's not going to cause harmful effects. Now, the EPA is continually reviewing those standards, and it's reviewed and updated about every 5 years. And so these drinking water regulations established by the Environmental Protection Agency are in response to kind of establishing, as it says, safe drinking water. Now, as well as these national standards, the Safe Drinking Water Act allows states to adopt their own standards, assuming that their own standards are at least as stringent as the EPA national standards. And so what you can see is that some states like California may have much higher regulations, much higher stringency for what qualifies as drinking water than other regions within the United States. So as you know from watching these ethical dilemmas before, I'm a big fan of science fiction and science fiction movies. Big fan of the book Dune and the Dune series by Frank Herbert. The latest rendition of a movie associated with Dune came out in 2021, and I wanted to include that in our discussion here today.
A still suit is a high-efficiency filtration system. Even this early in the morning, you wouldn't survive 2 hours without one of these. It cools the body and recycles the water lost to sweat. Your body's movements provide the power. Inside the mask, you'll find a tube to allow you to drink the recycled water. In good working order, your suit won't lose more than a thimbleful of water a day.
Most impressive.
So in this case, the Dune series of books and the movie are set on an arid desert planet without surface water available to it. It has very limited groundwater that is difficult to get access to. And so they're dependent upon using recycled water. Water is a very limited resource within this region. And so they're using individualized suits to recycle the water in these circumstances, much in the way that we're talking about recycling human-used water in replenishing or at least closing the loop on these human water use systems. So this gives rise to our ethical dilemma in science for this week. Should water conservation go beyond simply reduction of water usage? So in many cases, especially in Southern California, the American West, we're seeing they are in an extended drought, but we're also seeing droughts in other regions of the United States as well as other regions around the world. And so you have water restriction. You can't water your lawn. Talked about previously examples of an ethical dilemma where we're tearing out the lawns and replacing them in some way with drought-resistant plants. So in this case, is simply a reduction of water usage enough if we're looking at this very significant increase in demand and very severe limitations on the availability of fresh or at least clean drinking water for people? So to look at this a little bit further, should human water usage be focused on the use of recycled water rather than drawing from increasingly depleted surface or underground reservoirs? Should recycled water only be used for non-potable purposes? Potable water is water that is a quality of drinking water, and it is at the highest standards. But do we need that high quality of water to, water our plants? Or, even if we're not watering our plants, do we need that high quality of water to wash our dishes or to take showers? Should there be other uses for the recycled water and keep the purest water only for drinking? Finally, do additional standards or requirements need to be established so people feel comfortable drinking recycled water? In essence, right now, we probably are drinking recycled water because that water is going back into the surface water sources. It is going from water treatment plants into lakes or rivers where it will be potentially drawn into another water supply someplace else. And so these are just some basic questions that we need to think about as we focus in on the fact that water is becoming a much more limited resource, but it is a vital resource needed for life. So thank you for listening to this week's Ethical Dilemma in Science. Please see the description below for additional information and references. Thank you and have a great week.